Welcome to this problem explanation video. Today, we'll dive into problem number 2094, titled Finding Three-Digit Even Numbers. In this problem, we'll explore how to generate all valid three-digit even numbers using a given array of digits. Stick around as we analyze approaches, complexities, and the intuition behind solving this interesting problem. In this problem, we are tasked with finding all unique three-digit even numbers that can be formed from the given array of digits. The array, called digits, contains integers between 0 and 9, and it may have duplicates. When forming these numbers, we need to ensure two key constraints are met. First, the number must be a valid three-digit number, meaning it cannot start with 0. Second, the number must be even, which means its last digit has to be one of the even digits 0, 2, 4, 6, or 8. Once all valid numbers are identified, they should be returned in ascending order. The input is an array of integers, where its length can range from 1 to 100, and each element is between 0 and 9. The output is a sorted list of integers representing the valid three-digit even numbers that satisfy these conditions. Let's go through an example to better understand how this process works. Suppose the input array is digits equals 2, 1, 3, 0. From these digits, we can form a variety of three-digit even numbers, but we must filter out any invalid ones. For instance, numbers that start with 0, such as 023, are not allowed. Similarly, numbers ending with an odd digit, like 311, are also invalid. After applying these rules, the valid numbers we can generate are 102, 120, 130, 132, 210, 230, 302, and 310. Notice that these numbers are all three digits, they do not start with 0, and their last digits are even. Finally, these numbers are sorted in ascending order before being returned. Here's another example. If the input array is digits equals 2, 2, 8, 8, 2, we again need to form all possible three-digit even numbers while avoiding duplicates. After constructing the combinations, the valid numbers are 222, 228, 282, 288, 822, 828, and 882. It's important to note that even though the input array contains duplicate digits, the final output does not include repeated numbers. Additionally, the numbers are always returned in ascending order. The solution ensures that duplicates are handled properly and does not include redundant computations. Now, let's consider a case where no valid numbers can be formed. For instance, if the input array is digits equals 3, 7, 5, none of these digits are even. Since we cannot form any three-digit even numbers without at least one even digit, the output will be an empty list. To summarize, the solution should account for various constraints and edge cases. For example, if the array contains only zeros, no valid numbers can be formed. The solution must also handle duplicates and ensure that numbers with leading zeros, such as 023, are excluded. Finally, for larger inputs of up to 100 digits, the solution must remain efficient and avoid unnecessary computations while ensuring correctness. To begin solving this problem, we can consider a brute force approach. The intuition here is straightforward: generate all possible three-digit numbers using the digits provided in the input array, and then validate each combination against a set of conditions. First, the number must be a valid three-digit number, meaning the first digit cannot be 0. Second, the number must be even, which means its last digit must be one of 0, 2, 4, 6, or 8. Finally, the digits used to form the number must adhere to the frequency of digits in the input array. In other words, we can't use any digit more times than it appears in the input. To achieve this, we can use three nested loops to systematically generate permutations of the input digits, check each generated number against the conditions, and store unique valid numbers in a set. However, while this approach is simple and intuitive, its computational complexity is n cubed, where n is the size of the digits array. This makes it feasible only for small input sizes, as generating and checking all combinations quickly becomes inefficient for larger inputs. Now, we can refine our strategy by leveraging the problem's constraints to create a more optimized approach. Instead of generating all combinations, we focus specifically on valid candidates. First, we recognize that the first digit must be non-zero. This immediately eliminates many invalid combinations. Second, we know the last digit must be even, which further narrows down our options. With these constraints, we can iterate over the input digits in a systematic way. For the first position, we consider only non-zero digits. For the last position, we restrict our choices to even digits. The middle digit, being the most flexible, can be any remaining digit. Throughout this process, we track the frequency of digits in the input array to ensure that no digit is used more than it appears. By collecting valid numbers in a set, we maintain uniqueness without needing additional checks or constraints. This approach is still O(n) cubed in the worst case, but by avoiding unnecessary combinations, it is significantly faster and more efficient compared to brute force. An alternative approach could involve pre-computing all three-digit even numbers within the range of 100 to 998 and then filtering these numbers based on the input digits' availability and frequencies. While this method might be more efficient for very large inputs, it comes with its own limitations. Pre-computing all possibilities is memory-intensive and lacks flexibility, as it requires additional storage to maintain the pre-computed results. After evaluating these options, the optimized approach emerges as the best strategy. It balances simplicity and efficiency by leveraging the constraints of the problem. The critical insight here is to reduce unnecessary computations by systematically focusing only on valid candidates. By iterating over potential numbers and verifying their validity with frequency counts, we achieve a solution that is both clear and effective. This streamlined process allows us to solve the problem without the overhead of excessive memory usage or unnecessary complexity. When comparing the trade-offs between these approaches, the brute force method stands out as the simplest to implement. However, it quickly becomes inefficient as it generates a large number of invalid combinations, making it impractical for larger input sizes. On the other hand, the pre-computation-based approach is highly efficient for very large inputs but sacrifices flexibility and requires significant memory. The optimized approach strikes an ideal balance. By leveraging problem-specific constraints, it reduces computational overhead while maintaining clarity and adaptability. Although slightly more complex than brute force, it is much faster in practice and avoids the memory limitations of pre-computation. This makes the optimized approach the most effective and practical solution for this problem, offering a clear path to efficiently generate all valid three-digit even numbers while adhering to the input constraints. To solve this problem, we need to generate all unique three-digit numbers from a given array of digits, while satisfying three conditions. First, the number must be valid, meaning the first digit cannot be 0. Second, it must be an even number, so the last digit must be one of the even digits. Third, all digits in the number must come from the input array, with no digit used more than once. The algorithm starts with input validation to ensure the array is not empty and contains only digits between 0 and 9. This prevents unnecessary errors during computation. For example, if the input array is 1, 2, 3, we verify that all elements are valid digits. Next, we filter out the even digits from the array since these will be the only candidates for the last digit of the three-digit numbers. For instance, from the input 1, 2, 3, 4, we extract 2, 4 as the even digits. This step helps us focus only on valid candidates for forming even numbers, saving computational effort later in the process. Once the even digits are identified, we proceed to generate all possible three-digit permutations using three nested loops. In the outer loop, we select a digit for the first position. The middle loop selects a digit for the second position, ensuring it's not the same as the first. The inner loop selects a digit for the third position, skipping the digits used in the first and second positions. For example, given the input 1, 2, 3, we generate combinations like 123, 132, 213, and so on. After generating these combinations, we apply constraints to filter out invalid numbers. Specifically, we check that the first digit is non-zero and that the last digit is an even digit. For instance, with the input 0, 2, 4, combinations like 042 are excluded because the first digit is 0. By applying these constraints early, we eliminate invalid numbers without unnecessary processing. Finally, we store the valid numbers in a set, which automatically removes duplicates. For example, if the input is 1, 2, 2, 3, the set ensures that duplicate numbers like 122 are only stored once, simplifying the process of handling duplicates. The final step of the algorithm is to return the results in a sorted order. After all valid 3-digit numbers are stored in a set, we convert the set into a sorted list. This ensures that the output is presented in ascending order, which is both user-friendly and aligns with the expectations of many combinatorial problems. For example, if the input is 1, 2, 3, the output would be a sorted list like 123, 132, 213. This step is straightforward but important for providing a polished result. There are a few key insights that make this algorithm efficient. Using a set is crucial for automatically removing duplicates, simplifying the implementation. Filtering even digits early helps reduce unnecessary computations when generating permutations, as we only focus on valid candidates for the last digit. Finally, sorting the output ensures the results are consistent and easy to interpret, which is often expected in these types of problems. To implement this algorithm, we rely on two primary data structures. First, we use a set to store unique valid 3-digit numbers. This ensures that duplicates are automatically handled, which is both efficient and elegant. Second, we use lists to store the input array and intermediate results, such as the even digits extracted in earlier steps. Now, let's analyze the complexity. The time complexity is dominated by the process of generating all 3-digit permutations, which takes n cubed, where n is the size of the input array. Validating each combination is constant time, so this step doesn't add significant overhead. Sorting the output has a complexity of m log m, where m is the number of valid numbers, but since m is typically much smaller than n cubed, the overall time complexity remains n cubed. For space complexity, the set storing valid numbers requires m space, and the intermediate lists require n. Combining these, the overall space complexity is n plus m. This efficient use of time and space ensures that the algorithm performs well even for moderately large input sizes. This implementation solves LeetCode problem number 2094, finding 3-digit even numbers, by generating all valid 3-digit even numbers from the given array of digits. Step-by-step explanation. 1. Input and initialization. The function findEvenNumbers takes a list of digits as input. An empty set result is used to store unique 3-digit even numbers, and the length of the input array is stored in n. 2. Triple nested loops. The solution uses 3 nested loops to generate all possible 3-digit combinations from the input digits. The outer loop iterates over the first digit, the middle loop over the second digit, and the inner loop over the third digit. This ensures that all combinations of 3 digits are considered. 3. Index validation. Inside the loops, a condition checks if the indices I, j, and k are distinct to ensure that each digit is used only once per number. 4. Forming the number. For each valid combination of indices, a number is formed using the formula. Number equals digits, I, asterisk 100 plus digits, j, asterisk 10 plus digits, k. This constructs the 3-digit number from the selected digits. 5. Validating conditions. The first digit, digits, I, must not be 0 to ensure a valid 3-digit number. The last digit, digits, k, must be even, as the number must be even. If both conditions are satisfied, the number is added to the result set. 6. Sorting and returning results. After all valid numbers are identified, the set is converted to a sorted list and returned. Sorting ensures the numbers are output in ascending order. Complexity analysis. Time complexity. The triple nested loops iterate in n cubed, where n is the length of the input array. Since n is small, maximum 10, this is efficient. Space complexity. The space usage is k, where k is the number of unique valid numbers stored in the result set. This approach guarantees that all valid numbers are identified and returned in sorted order while avoiding duplicates. Here, we start by importing the necessary libraries and defining our solution class with the method findEvenNumbers. This method takes an integer array digits as input and aims to find all unique 3-digit even numbers that can be formed using those digits. Inside the method, we first declare a set called ResultSet, which will store the valid numbers to ensure uniqueness. We also determine the length of the digits array for iteration. Now, we use 3 nested loops to generate all possible permutations of 3 digits. The indices I, j, and k represent the positions of the digits we are combining, and we ensure they are distinct by checking that I, j, and k are not equal to each other. For each valid combination of indices, we calculate the number by multiplying the first digit by 100, the second digit by 10, and adding the third digit. Next, we impose two conditions to filter valid numbers. First, the leading digits, I, must not be 0 because a valid 3-digit number cannot start with 0. Second, the last digits, k, must be even since we are only looking for even numbers. If both conditions are met, we add the number to the result set to ensure we only keep unique results. Once we have generated all valid 3-digit even numbers, we need to prepare the final output. To do this, we first convert the result set into a list called result list. This allows us to use the collections.sort method to sort the numbers in ascending order. Sorting ensures that the output matches the expected order. After sorting, we need to convert the list into an integer array, as the return type of the method is int. We declare an array called result with the same size as result list and use a simple for loop to copy each element from the list into the array. Finally, the result array, which now contains all the unique 3-digit even numbers in sorted order, is returned as the output of the method. To solve this problem, we begin with the input digits, which in this case are 2, 1, 3, 0. First, we initialize an empty result set to store the unique 3-digit even numbers we generate. The total number of digits available, n, is 4. Next, we generate permutations by iterating over all possible combinations of 3 distinct indices I, j, and k. For each combination, we form a 3-digit number using the digits at those indices and check 2 key conditions. The first digit must not be 0, and the last digit must be even. For example, when I equals 0, j equals 1, and k equals 2, the digits used are 2, 1, and 3. This forms the number 213. Checking the conditions, the first digit is not 0, which is true, but the last digit is odd, so the number is not added to the result set. However, when I is 0, j is 1, and k is 3, the digits used are 2, 1, and 0, forming the number 210. Both conditions are satisfied here, so 210 is added to the result set. Now, we continue generating permutations. For the combination where I equals 0, j equals 2, and k equals 3, the digits used are 2, 3, and 0, forming the number 230. Again, both conditions are satisfied since the first digit is not 0 and the last digit is even. Therefore, 230 is added to the result set, which now contains 210, 230. This process continues for all valid index combinations, checking each number against the conditions before adding it to the result set. Once all permutations are evaluated, we sort the result set in ascending order to ensure the output is structured correctly. The sorted result for this example is 120, 130, 210, 230, 310, which is returned as the final output. In the second example, the input digits are 5, 7, 2. As before, we initialize an empty result set and note that the number of digits, n, is 3. We then generate permutations by iterating over all distinct index combinations. For the combination where I equals 0, j equals 1, and k equals 2, the digits used are 5, 7, and 2, forming the number 572. Checking the conditions, the first digit is not 0, and the last digit is even, so 572 is added to the result set. For another combination, where I equals 0, j equals 2, and k equals 1, the digits used are 5, 2, and 7, forming the number 527. Here, the first digit is not 0, but the last digit is odd, so 527 is not added to the result set. The result set at this point contains only 572. We continue evaluating all valid index combinations, ensuring that each number satisfies the conditions before including it in the result set. Once all possibilities are exhausted, the result set is sorted to produce the final output. In this case, the sorted result is 572, which is then returned. Moving on to the third example, the input digits are 0, 4, 6, 8. Again, we initialize an empty result set and note that the number of digits, n, is 4. We proceed to generate permutations by iterating over all valid index combinations. For each formed number, we verify that the first digit is not 0 and that the last digit is even. For the first valid combination in this example, where I equals 1, j equals 0, and k equals 2, the digits used are 4, 0, and 6, forming the number 406. Both conditions are satisfied here, so 406 is added to the result set. For another combination, where I equals 1, j equals 2, and k equals 3, the digits used are 4, 6, and 8, forming the number 468. Again, both conditions are satisfied, so 468 is added to the result set, which now contains 406, 468. This process continues for all valid index combinations, adding each qualifying number to the result set. Finally, we sort the result set to produce the output in ascending order. The sorted result for this example is 406, 408, 460, 468, 480, 486, 604, 608, 640, 648, 680, 684, 804, 806, 840, 846, 860, 864, which is returned as the final output. To analyze the time complexity of this algorithm, we start with the process of generating all possible 3-digit permutations of the input list. This involves 3 nested loops, each iterating over the n elements in the digits array. Since each loop runs independently through all elements, the total number of iterations is the product of these loops, which gives us O, n, asterisk O, n, asterisk O, n, or O, n cubed. Within the innermost loop, the algorithm performs a check to ensure that the indices used to select the digits are distinct. This operation is a simple comparison and takes constant time, or O1. Additionally, the algorithm forms a 3-digit number and verifies that the first digit is non-zero and the last digit is even. These arithmetic and logical checks are also O1 operations. Together, these steps mean that the dominant factor for time complexity comes from the cubic scaling of the nested loops. After generating potential numbers, the algorithm inserts valid 3-digit even numbers into a set. The insertion operation in a set is amortized constant time, or O1. Since the total number of unique valid 3-digit even numbers is limited to 900, the cumulative cost of all insertions is proportional to this maximum, making it a negligible component compared to the cubic growth of the loops. Once all valid numbers are stored in the set, the algorithm sorts them to form the final output. Sorting a collection of size m, where m is the size of the set, takes O, m asterisk log, m, time. With m being at most 900, this step has an upper bound of approximately O, 900 asterisk log, 900, which simplifies to O, 9000. However, this is constant relative to the cubic complexity of the nested loops, meaning the final time complexity of the algorithm remains O, n cubed. The space complexity of the algorithm is determined by the structures used to store data during execution. The set result is used to store unique valid 3-digit even numbers. Since the maximum number of such numbers is 900, the space required by the set is constant and does not scale with the size of the input, making it O1. The input array digits is stored in memory and has a size of O, n, which is proportional to the number of digits provided as input. Additionally, sorting the unique numbers requires temporary storage, which is O, m, where m is the size of the set. Since m is capped at 900, this space usage is constant relative to n. Therefore, the dominant factor in space complexity is the storage of the input array, resulting in a final space complexity of O, n. When comparing this solution to a naive brute force approach, the improvements become clear. A brute force method might involve generating all 1000 numbers from 000 to 999 and checking whether each number can be formed using the input digits. This would involve O, 1000, checks for each number, leading to a time complexity of O, 1000 asterisk n, which is significantly less efficient. In contrast, the proposed algorithm narrows the search space by directly constructing valid 3-digit numbers using the input digits, bypassing unnecessary checks. While the cubic time complexity of O, n cubed, is not optimal for very large values of n, it is efficient and well suited for the problem's constraints, where n is typically small. Overall, this algorithm balances efficiency with simplicity, achieving O, n cubed, time complexity and O, n, space complexity. It avoids the pitfalls of brute force methods and focuses computational effort on generating only valid permutations. When working on this problem, there are several common mistakes to watch out for. First, not handling edge cases can lead to runtime errors or incorrect results. For example, if the input array is empty, contains duplicate digits, or has fewer than 3 digits, your solution might fail unless these scenarios are explicitly accounted for. Always make sure to confirm the input constraints and test these edge cases thoroughly. Another frequent mistake is generating invalid combinations, such as numbers with leading zeros or repeating digits, when the problem requires unique digits. This can often happen if the combination logic isn't carefully aligned with the problem's rules. Inefficient brute force methods are another pitfall. If you generate all possible combinations without filtering out invalid ones early, the computational cost can grow significantly, especially with larger input sizes. Instead, aim to optimize by eliminating unfit candidates as soon as possible. Additionally, pay close attention to the return type. For example, if the problem expects a list of numbers but you return a count or vice versa, your solution will not meet the requirements. Lastly, watch for off-by-one errors, which are common in range-based logic. These errors can occur if you use inclusive bounds when exclusive ones are needed. Double-check your loop conditions and index calculations to avoid this issue. In an interview setting, this type of problem offers a great opportunity to demonstrate key problem-solving skills. One of the most important is pattern recognition. Many problems involving combinations or permutations require you to identify specific constraints, such as ensuring unique digits or adhering to a fixed range. By recognizing these patterns early, you can reduce the search space through strategies like early filtering or backtracking. Using data structures like sets or hash maps can also be a game changer here. Sets are excellent for avoiding duplicates, while hash maps enable quick lookups when validating combinations. Another crucial skill is communication. As you work through the problem, clearly explain your thought process, especially how you're generating combinations and why you've chosen a particular algorithm. For example, you might justify using brute force with pruning or opting for a more direct mathematical approach. Interviewers will also pay attention to your ability to test your solution extensively. Make sure to discuss the edge cases you'd use to validate your implementation. It's a great way to show thoroughness. Finally, it's helpful to be aware of related problems, such as generating all permutations, handling duplicates and permutations, or creating subsets with specific constraints. These problems often share techniques and can inform your approach. There are also alternative approaches to solving problems like this, each with its own advantages and trade-offs. Backtracking is a highly efficient method for generating combinations or permutations with constraints. It works by pruning invalid combinations upfront, which saves computation time. However, backtracking requires careful implementation, as debugging the pruning conditions can be tricky. Another option is the mathematical approach, where you calculate results directly using combinatorics or arithmetic. This method can be very efficient when the constraints allow for it, but it's not always applicable, especially if enumeration is necessary to meet the problem's requirements. Bit masking is another alternative that's particularly useful for problems involving subsets or combinations. By using bit representation, you can systematically generate all possible subsets. However, this approach can be unintuitive for beginners and may be difficult to debug. Lastly, dynamic programming is worth considering if the problem has overlapping subproblems, such as counting subsets with specific properties. While DP can be powerful, it may require additional space, and for smaller inputs, it might not always offer a significant speed advantage over backtracking. Understanding these tools and knowing when to apply each one is key to tackling a wide range of problems effectively. To wrap up, this problem highlighted the use of combinatorics to generate and validate 3-digit numbers from an input array. We reviewed the brute force approach and its limitations, while emphasizing how to evaluate efficiency and handle edge cases. Thank you for your time. Don't forget to like and subscribe for more insights into solving coding problems. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!